Okay, so we're live here. So welcome to lesson 2. So folks, today I would like maybe a little more participation. So, at some point I may just call on you, but if we can get a few more people to be involved in the class, that would be great. All right, so I just want to recap where we ended off last time. So we saw last time that we could think of numbers as vectors, okay? That you could think, as we said, you take the number 5 and actually think of it as the vector 5, which starts at 0 and ends at 5. And so when we try to apply this system to operations, okay, so, if you want to think about 5 plus 3, which has to give you 8, you realize that the way you could do that by thinking of these numbers as vectors is to place the vectors tip to tail, and then the resulting vector. And what I mean by the resulting vector, meaning the vector that starts at the tail of the first and ends at the tip of the second, gives us this vector 8, which is what we expect when we add 5 and 8. And we saw that you can think of subtraction of vectors in a similar way as adding the negative. Okay, so if I want to subtract vector 2 from vector 5, well, we do the same thing. It's the same as adding the opposite number, or in this case here, the opposite vector. So if I add to the vector 5 negative vector 2, I just get vector 3, which is what I expect when I subtract 5 minus 3. Okay? So what this does is hopefully gives us a way to think about addition and subtraction when we move to beyond 2 dimensions, where we can't necessarily make this connection between the number line and vectors. All right, so what we have here, so let's go to the worksheet, is they ask us, okay, and you'll notice here they put it in an application context, but if you take a look at part A, they're essentially asking us to do the same thing, okay, because we see that the boat is moving in the east direction because of the current, 3 meters per second, okay, and then we have another thing that's going to propel this boat in the exact same direction. So when you think about it, it's a one-dimensional problem, all right, whereas in B, says suppose that the velocity of the wind were 5 meters per second north 30 degrees east. Well, that's when you realize that they're not in the same direction. All right. And then in part C, they give you another thing that's propelling this boat. Okay, the person now starts rowing. So what I want you to do is I want everybody to take a couple of minutes to draw diagrams. All right, and we'll take this up in a minute. Okay, so again, give you a minute to work on that. And ask questions as you go along if you have any. Yes, assume that it is. All right, so let's take a look at these examples here. And if I take a look at this first one, well, again, I've got this vector that I'll call B for this first vector that's given. That's 3 meters per second in the east direction. And then I've got the wind, which I call W. All right, and if I want to add them together, if I wanted to see what the effect is of combining both of those vectors, well, I use my conjecture from the number line, is that I take my vector b, I place a double vector w tip to tail, and then the vector that goes from the tail of the first to the tip of the second represents the resultant of these two velocities. So that in the end, this boat would be traveling at 8 meters per second. And this resultant of combining these two vectors is how we define addition. Okay? Now, if we take a look at the next one, we see that for the first time, we're not in a one-dimensional world. Okay, so now we're in a two-dimensional world. So I still have my vector b that's moving, that's going in the east direction, but a lot of you will be familiar with this. When I have to now draw the second vector tip to tail, you notice how I draw a little cardinal plane at the start of my second vector, because I'm going to be placing this second vector at the tip of the first. Okay, and so here I see north 30 degrees east, so I start north and I go 30 degrees towards the east direction, and then I draw my vector, and again using that lead we got from one-dimensional vectors, the resultant just goes from the tail of the first to the tip of the second, and this is how we define vector addition. All right, so here we're going to be working in 2D for at least most of this unit here, but we're going to see that this idea of how we add vectors can then just extend to 3D. Okay, we're going to run into a bit of a problem when we try to think of this in terms of 4, 5, 6 dimensions, because we don't have that physical idea of being able to place two vectors tip to tail. All right, so let's take a look at the next one. The next one just kind of takes that further. Okay, so here now we've got b. We're still adding the vector w, tip to tail. And then again, once I want to add that vector, what I call p, for the person rowing, again, look what I do. I draw my cardinal plane, okay, east 20 degrees towards the south. And then from there, the resultant vector, what we consider the sum of these three vectors, starts at the tail of the first all the way to the tip of the last. All right. So this is our general way of thinking of vector addition. All right. So let's consider perhaps another way of looking at this. All right. So let's bring up our worksheet again. And here, do you have to label it as the resultant vector? Again, your diagram is going to be mostly used to solve a problem. So what you put in the diagram, if I ask you to draw the picture, if that's part of what I'm asking you to do, then yeah, you should label the resultant vector. Okay. So here I'm asking for two ways of representing the idea of the sum of two vectors. Okay. And now you'll notice my next question, I'll talk about that right away, is, hey, when we're talking about operations on mathematical objects, we start to think about what types of properties they might have. And certainly one of the ones that we've talked about a lot is commutativity. All right. So I think we probably expect this to be a commutative operation, but let's at least justify it. Now you'll notice here I'm going to use the words justify a lot because we don't quite have a really good way of representing vectors that allows us to prove these things. We will get there though. All right. So let's go back here, and now I'm working with these vectors in 2 dimensions. And so I've got, my vector u, okay, and I've got my vector v, okay. I place them tip to tail, right? And here I have my vector u plus v. Okay, so this is the representation of the sum of vectors, which we've already seen. This is called the tip to tail method. All right, and of course I can do this with multiple vectors. Okay, when I'm adding 2 vectors in particular though, okay, there's another way in which we can consider this addition. Okay, so here, if I take the vectors tail to tail, okay, if I take these vectors tail to tail, Well, now I realize. Now, what was special about placing them tail to tail? What did we? Where did that come into play? Where we wanted to look at them tail to tail?
When
Yeah,
we were
remember. Yeah, go ahead.
when we were looking at the angle between them.
Exactly. That's how we defined the angle between two vectors. Okay, is they had to be placed tail to tail. So if a question is given, and as we're going to see later on this worksheet, that sometimes that's how the information is given. I don't explicitly say, U is 20 kilometers east, 20 degrees north. I'm going to give information about the angles with the vectors with respect to each other. So another way in which we can look at this is when we place the vectors tail to tail, is that the sum, okay, is the, and again, notice I'm using the same vector, the sum is the diagonal of the parallelogram formed by the two vectors starting from the two tails, okay? And we see it gives us the exact same result as before, okay? So this is our second way of representing the sum of two vectors, is as the diagonal of the parallelogram formed by the two vectors being placed tail to tail, all right? So the next thing they ask us in number 4 is to justify that the addition operation on vectors, as we've described them, is commutative. Okay, so again, take a minute to draw yourself a diagram. Again, this is going to be a pictorial justification of why two vectors that are being added can be added in any direction, meaning you can add u plus v, or you could add v plus u, and you'll get the same result. All right, so go ahead and take a little bit to draw that out. Okay, so let's come back together here and take a look at this. And hopefully what you did is one of two things, okay? Is you might have drawn the diagram and said, well, let me take u plus v, okay? And you might have drawn two different scenarios, u plus v, and then you got to your resultant here. But then the other thing you could do is take v and add to that u. So notice here, v is the one that's coming first. I'm doing v plus u, or I do u plus v, and I get the exact same result. So essentially, remember our old parallelogram. Our parallelogram method essentially shows to us that this is a commutative property, because whether I do u plus v or I do v plus u, I get the same result, okay? Which is, again, what we anticipate. Remember that this whole idea was based on using our view of real numbers on a number line to give us an idea as to where to go forward. All right, so now what I'd like you to do is to think about subtraction, okay? So what would the subtraction of two vectors, in this case here, 2 dimensions, look like? Okay, and are there any relationships that you might find? Is subtraction commutative? I think we all know what we hope the answer is going to be, okay? And might there be any interesting relationships that we might find involving subtractions, the way we were able to find this idea with vector addition, that we were able to make this connection to the parallelogram. And that's the hint I'm giving you here. is, can you make a connection to the parallelogram formed by the two vectors? All right. So I'm going to give you a bit of time to work on number 5 and number 6, and let's see what we can come up with, okay? And as you're working on it, I'll take questions from the chat, or you can even just say them out loud. All right, so I'm going to give you about 3 minutes to work on questions 5 and 6. Again, you're using diagrams. See where you can go with that. Okay, so folks, let's come back to this here. All right, so let's take a look at, we had a comment there. Okay, so it could be considered commutative because we just rearranged subtraction of vectors into addition of vectors, right? Well, let's take a look. That'll be interesting to see if that ends up being the case, all right? So let's take a look here. So we talked about vector subtraction as just being adding the opposite. So let me take the opposite of v, okay, which is this vector there, and let me add it to the vector u. Okay, so there you go. Nothing too fancy here. Go from the tail of the first to the tip of the second. There you go. And there's our vector subtraction. Okay, so this is how we would subtract two vectors, is just add the opposite. Okay, nothing too fancy. But if you take a look at this parallelogram, sorry, if you take a look at this diagram, I kind of gave you a hint that there might be some relationship with the parallelogram formed by the two vectors. Can anybody see what might be special about this vector u minus v? I want you to take a look at that diagram and see if there's something special related to this parallelogram. Okay, I'll give you a little hint. Remember, vectors can be moved around wherever you like. Okay, and I see, there you go. And we notice that if I take this vector and I just move it over, it's exactly the other diagonal of the parallelogram. So that's pretty nice, except now it's the diagonal that joins the two tips. Remember that addition was the diagonal that started at the two tails and went to the other corner. But here we see that it's just going from one tip to another. Now, one of the things we asked was, well, is this commutative? Well, let's do it the other direction. Okay, so let's take vector v and add to that the opposite of vector u. Okay, so there you go. Let's take that there. And we have our resultant going from the tail of the first to the tip of the second. And we realize that there is still this connection between the diagonal, because if I take this resultant now and I just move it over, I get again that same diagonal. What's the difference though between u minus v and v minus u? It does definitely produce the other diagonal, but there you go. You realize that they have opposite directions. So while u minus v are not equal, so we've just proven, well, sorry, I should not use the word proven. We've justified that u minus v and v minus u are not the same, so it's not commutative. But what we see is that u minus v and v minus u are opposites to each other, which is kind of what we expect, because when you think of 5 minus 3 and 3 minus 5, one gives us 2 and one gives us negative 2. So it gives us opposites. So what we're seeing is that this way of defining vector addition and subtraction seems to be working out the way we expect it to work out. Even when we're now putting it in this two-dimensional context, we're still getting those results that we were getting back in one dimension. All right. So before we start looking at some problems, let's take a look at our notes here and see what we've come to. All right. So just a reminder that our first operation that we used with vectors was this idea of multiplying it by a scalar. Okay. And what it does is scalar multiplication just gives you a parallel vector, okay, whose direction is either the same or opposite, depending on whether k is positive or negative. And the magnitude of the new vector was just the absolute value of k times the magnitude of the original vector. All right, now we get to vector addition and subtraction. So we see that vector addition can be seen in two ways. It can be seen as adding tip to tail, so one vector after the other, and the resultant is just given by the vector going from the tail of the first to the tip of the second. Or this parallelogram method is placing them tail to tail, and then the sum is just the diagonal starting at the two tails of the parallelogram that's formed, okay? Whereas vector subtraction can be seen either as adding the negative or adding the opposite of the second vector, okay, and then doing tip to tail. So u plus negative v gives us our resultant. Or if u and v again are placed tip to tail, we have that u minus v is just the diagonal, okay, that joins the two tips. But what's very important here, and I think I have it right here, that this diagonal that's formed by the subtraction is not the same whether I do u minus v or v minus u. Notice here what it's doing. It's going from the tip of v to the tip of u. So the way I describe this is I say it's going from the tip of the second to the tip of the first. All right? And if we look at, our example here, we see that when we look at u minus v, goes from the tip of v to the tip of u, so the second to the first. And when I look at v minus u, it goes from the tip of u to the tip of v. In other words, the tip of the second to the tip of the first. All right? So two ways of considering vector addition and vector subtraction. And you have to imagine that we would likely consider these two different scenarios depending on how the information is given to us. And this is where, before I give you some time to work on it, let's take a look at the examples that we've got. Okay, so you notice here I'm asking for u plus v and u minus v. Okay, but the vectors are given using this cardinal notation. So in other words, where I give you the specific magnitude, and then I give you the direction of the vector based on north, east, south, and west. Okay, same thing for v. Whereas in number 8, the information is given differently. I'm explicitly giving you the magnitudes, but the direction is given in a relative way. I give you the direction with respect to each other. We say that the angle between u and v is 40 degrees. Okay? So you have to imagine that in this scenario, you might want to start off your problem in tail-to-tail fashion, whereas in this problem here, you probably want to add them or subtract them tip to tail. Okay? So what I'm going to ask you to do is I'm going to ask you to work on number 7. Okay, and the main thing I want you to see, what I would actually like you to start doing is start with a diagram in each, so that even if you don't get to all the math, okay, so what you should be doing here is at least getting the diagram for each. All right, so I had a good question here that I want to take a look at. Whoops. Sonia asks, as a general standard, are we having 1 unit equal 1 centimeter when drawing? So the question I have for you, and maybe somebody can tell me why I'm not going to worry about that at all. Okay? Why am I not going to worry so much about scale? So Sonia, can you think about why, in the end, when I'm drawing this picture, I'm actually not going to worry about the scale at all? There you go. So good answers is that the diagrams are just a guide. Okay, the last thing you want to do, and I know in a physics class you often start by using a scale and adding and subtracting these things, you know, by measuring them and using protractors and the whole thing. However, here we want to focus purely on the mathematical way of, or at least arithmetic way of adding these things. So we are only using these diagrams as a guide. Now, having said that, when you're drawing a vector of length 30 and a vector of length 20, you should be making a bit of an effort to make this one a little longer than that one, just so that the diagram seems reasonable. When you're using an angle of 20, try to be reasonable with it. Make sure it doesn't look like an angle of 60. All right? So I'm going to give you maybe 4 minutes to just set these problems up. So I'm not going to, don't worry so much if you don't solve the whole thing. The idea is to get it set up. All right? So we'll give you a bit of time to work on that. All right, so let's take a look at the part A, where I'm adding them together. Now, given the way these things are defined, I'm going to use a tip-to-tail method. So we see that the first vector, okay, u, is equal to 30 east 20 degrees north. So 30 east 20 degrees north. Okay, so I think we already talked about how we would set this up. So we're going to use our little cardinal plane. Okay, and here's east, so I'm going to go 30 degrees north. Again, I'm going to make no effort to be exact, but I am going to try to, you know, be reasonable. So there's my 30 degrees. And then if I want to add the second vector, v, which is 20 north 10 degrees east, well, what I want to do is I want to place the next vector at this tip. Okay, so what we're going to do is just draw ourselves another little cardinal plane there, and we have north 10 degrees east. So I'm going to have my second vector, again, make it a little shorter since it's only 20, and this here is going to be equal to 10. Okay. Say that again. It should be 20 degrees. What did I write? 30. Oh, thank you very much. I guess I was looking at the magnitude there. So 20 degrees. All right. Okay. And so now my resultant vector is going to start at the tail of the first to the tip of the second. Okay. And there's my resultant vector. All right, so now the question is, how am I going to find this vector? So a couple of things to remember is that when you're determining a vector, it's not just enough to find the magnitude, is you also have to find the direction. All right, so this is where, now I know some of you solve these problems in a different way. We'll make reference to that a little later on, but for those who haven't done physics, I think I'm just going to stick with one method. And for those of you who did something different in physics, it's good, you know, get to see something done a little differently here. All right. And one thing I see is that when I add two vectors together to get a resultant third, well, I end up with a triangle. Okay. And so I can use trigonometry here. So if I have my magnitude here of 30, that's a side length. My magnitude here is 20, there's another side length. Ideally, what I would like here is an angle inside this triangle. And this is where now you have to go back and remember a lot of your just basic geometry rules, okay? And what I see here is I see this line is parallel to that line. So if this is 20, then this must also be 20, okay? And north and west are at 90 degrees to each other. So in the end, I can see that I've got this whole angle. Okay, it's just 90 plus 10 is 100 plus 20 is 120 degrees. Okay, and so now what I've done is I've got a triangle where I've got two sides and an angle, and we know that that's enough to solve the triangle. Okay, so which of our rules are we going to have to use here? Somebody just quickly tell me what's going to be applicable. There you go. It's going to be cosine law. Good. So if this is vector u plus v, okay, I want to make sure my notation is good. The magnitude of u plus v is just going to be equal to, well, the square root of the sum of the square of the opposite two sides. So 20 squared plus 30 squared minus 2 times those two other sides. So 20 times 30 times the cosine of the angle opposite, the u plus v. So cosine of 120. Okay. And if you calculate that, okay, I have it calculated here on the side somewhere. Where does it? Looks like it's 43.6 units. Okay. So now I have the magnitude of this vector. What I need is a direction. Okay. Now again, if we're going to talk about using directions using these cardinal planes, what I need is a cardinal plane at the tail of the vector that I'm trying to describe. I already have a cardinal plane at the tail of the vector that I'm trying to describe. Okay, it's the same as the tail of that first vector. Okay, so what I'd like to do is I'd like to reference this vector compared to one of these axes. And it looks like what I'm going to use is I'm going to use this vector here. Okay, but this vector that relates u plus v to the east direction is not inside my triangle. But what is inside my triangle is this vector theta. Okay, so this vector theta, and then all I have to do is add 20 to it, and then I'll be able to describe the direction. Okay, so now I'm going to look for this vector theta. Now, as I'm doing what I'm doing, don't yell at me, okay? But I want you to try to explain why I'm doing what I'm doing, all right? So what I'm going to do is I'm going to use the cosine law to find this angle because I know the other three sides, okay? So it's going to be cos inverse, okay? So I'm just kind of going backwards on my cosine law. So cos inverse of, well, what am I going to have? This is the angle I'm looking for, so this is the opposite side. This is 20 squared. And then if I was thinking about the cosine law, I'd be bringing to the other side of the equation the other two sides. So minus 30 squared minus 43.6 squared, okay? And then I'd be dividing by this whole thing here, by the negative 2 times those other two sides, 30 times 43.6. Okay, and if you put that into your calculator, okay, if I did it correctly, it should be 23.4 degrees. All right. And so now, if I want to describe this vector relative to the east direction, I'm just going to add 20 to it. Okay, so now I can say that the vector u plus v is equal to, okay, my magnitude, 43.6, and then my direction is going to be east, 43.4 degrees north. Okay, and there we go. So the big question I have before we move on is, why did I use the cosine law? And why did I not just use the sine law? Because you certainly have enough information to use the sine law. Okay, and you know, I mean, once you kind of know this formula well, the cosine law is not that much more difficult, but there's an argument to be made that the sine law is a little faster. So can somebody give me a reasoning as to why I did not use the cosine law? Sorry, why I didn't use the sine law? Okay, maybe I'll give you a bit of a hint that if I were to use the sine law, okay, let's say I were to write it down. So here I would have sine of theta equals sine of theta over its opposite side 20 is equal to the angle that I know, sine of 120 divided by its opposite side, 43.6. So in other words, I'm using two sides and one angle, okay? And Gleb, of course, remembers that when you're using the sine law with two side lengths and an angle, we have the possibility of the ambiguous case, where you could conceivably have two answers. All right. Now, there's an argument to be made that if I solve this and I get 23.4, then I can reason out, well, here, I can see from my diagram that this angle is definitely acute, so I don't have to worry about being the obtuse angle. But then the problem is I have to make sure I've got a very precise diagram. If I'm not drawing a good diagram, it might not necessarily be, let's say the two answers are 89 and 91. On a diagram that I'm drawing very quickly, it might not be easy to see which of those two it should be. And so the rule should be that anytime I have the option to use the cosine law, I should just be using the cosine law. Okay, so that I don't even have to think about checking whether the ambiguous case is even an issue. I don't need to check if it is an issue, which of the two answers it should be equal to. The cosine law has no ambiguity to it. So my big suggestion is when you have the option to use the cosine law, okay, then you should definitely use the cosine law. Now remember that this is not an issue if I'm working with two angles and one side length, because once you're using two angles, it fixes the triangle. Okay, any questions on that as to why? Yeah, of course you need to be aware, because, and this is in fact why I use the cosine law, since I had that option, so that I don't even need to think about the ambiguous case. All right, so I would definitely keep that in mind. All right, so let's take a look at the subtraction. Okay, now here there's a couple of ways of drawing this out for the subtraction. Okay, so one way to draw it out. Oh, wait, sorry, I just realized I shouldn't be drawing anything that. Okay, so here. So I'll draw the way I'm not going to use first. So if I take U, I again have 30 east, 20 degrees north. So I have this angle here, and again, this is 20, and that's a length of 30. And then what I could do is I could add to that the negative of this angle. So who can tell me what the opposite of this angle is going to be? So remember, this was north, 10 degrees east. There you go, it would just be the opposite. It would just be south, 10 degrees west. Okay, so again, I put my little diagram, and I have south 10 degrees west. And there you go, 10 degrees. There's my length is 20. And so now I can draw my resultant vector. So that is one way to draw the vector, or the subtraction. Another way is to, again, start with my first vector here. But what am I going to do now? So Kieran asks about whether it's east 80 degrees north or north 10 degrees east. Doesn't matter. Either one of those is acceptable. I know some people prefer not having angles that are greater than 45, but I'm not going to be picky about that. What's the other thing I can do here if I want to write this in a different way?
You can attach the other one from the same starting point.
There you go, is draw them tail to tail. Okay, so I can draw the second vector, okay, here. So east 10 degrees north. It's going to be a little shorter. Okay, and then from there, draw the tip-to-tip method. But since I'm doing U minus V, I'm going from the tip of the second to the tip of the first. So that would be my vector. All right, so this is 10 degrees, but the side length is 20, the side length is 30. And so now what I'm looking for is I'm looking for this magnitude. And yet again, I've got a nice triangle to work with. And this is where I'm just going to use my knowledge of trigonometry. Here I've got a right angle, 10 degrees and 20 degrees. So 90 minus 30 is just going to be 60 degrees. And there we go. Now I've got a triangle that I can work with. So this is u minus v. So if I'm finding the magnitude of u minus v, now notice how I'm being careful with my notation. When I'm calculating a side length, make sure you are referencing the magnitude of that vector. So again, here, and the idea is to just become really fast at this, okay? 20 squared plus 30 squared minus 2 times 20 times 30, okay? Cos of 60 degrees, all right? So let's calculate that here. What do we got? Square root of 20 squared plus 30 squared minus 2 times 20 times 30 times cos 60. Okay. So we have 26 point, I guess, 5. Okay. Okay. Now, as I did before, when I'm looking, I'm going to look for an angle now. Now, remember that this is my, sorry, I'm working with this diagram. Sorry about that. That this is my diagram here. So this is the tail of my resultant vector. So as before, I'm just going to work with the, I'm going to put a little cardinal plane there. And so what I'd like to do is I'd like to use this angle here. This is what I would like to work with. But of course, this is not the angle that's in the triangle. But hey, look at what I have here, similar to before. Parallel lines, that if this is 10, this is also 10. So if I find this angle in the triangle, oh, it froze there for a second. If I find this angle theta in the triangle, I just have to subtract 10 to get the angle that I'm looking for. Okay, as before, I'm going to use the cosine law, cos inverse of. So its opposite side is 30. So 30 squared minus the square of the other two sides. So minus 20 squared minus 26.5 squared all over negative 2 times 20 times 26.5. And then here, let's see what I've got. Okay, cos inverse of, make sure I put brackets around the numerator, 30 squared minus 20 squared minus 26.5 squared. Okay, close my bracket, divide by the denominator. Again, open a bracket, negative 2 times 20 times 26.5. Okay, and it looks like we get an angle of 79. Okay, but of course, 79 represents this whole angle here. I want to subtract. I want to subtract 10 in order to get just the angle from the south direction. So u minus v is going to be equal to 26.5, and then south looks like it's 69 degrees east. Okay, now as somebody referenced before, we could write that another way. We could write that as 26.5 and instead go east, okay? And 90 minus 69 will be 21, east 21 degrees south, okay? So I'm not picky about whichever one you use, okay? Some people prefer this angle to be less than 45, all right? So just take a quick look at number 8, okay? I'm not going to go through all the solutions written out. We'll just take a look at the solutions together. But let me give you just a couple of minutes to consider how things would change if the information is given in this way. So again, what I would suggest maybe you do is you try to draw the diagrams correctly. Okay, and then from there we'll take up the quickly together. All right, so I'll give you 3 minutes to work on that. All right, so let's come back together here. So let's take a look at this first one. And there's a couple of things that we have to consider in these questions that are a little different. All right, so I want you to ignore this now because the information that's given is with the angle between them. So the first thing that I drew was the vector with magnitude 4, then the vector with magnitude 7, and the angle between them is 40 degrees. Okay? But what I'm trying to do is I'm trying to calculate the magnitude, or I'm trying to calculate the vector that's the diagonal of the parallelogram formed by these two vectors. But instead of trying to figure that out, all I did is I took this vector with magnitude 7 and I moved it so that it's tip to tail with the first vector. Okay, and again, that's the great thing about vectors is I can move them around as I wish. So I just took this vector 7 and I moved it over so that it's tip to tail to the vector u. All right? But this is the important thing, because sometimes if we want to just jump into doing the calculations, we might want to work with this angle 40. Okay? So while 40 is the angle between the two vectors when they're tail to tail, once I move it over so that they're tip to tail, the angle inside the triangle is not 40. But this, again, of course, we're just using good old, basic geometry, is when I move this vector over, it's still parallel to each other. So we just use the parallel line principle, which says that the acute angle is going to be the supplementary angle to the obtuse one. So here, if this was 40, this angle here is 180 minus 40. Which is 140. Okay, so make sure that you're working with the angle that's actually inside the triangle. So from there, as before, I just use the cosine law because I know the two other sides in the opposite angle. And then what I decided to do is, well, since I've already got this triangle written out, hey, let me find this angle theta. This is the other thing that's a little different about this problem, is how do we define the direction? So let's start by finding this angle theta. So again, I use the cosine law just to kind of cover my bases to make sure I don't have to worry about ambiguous case. Okay, and look at how I define the direction. I just define it with respect to the two vectors that I'm given. So what I said is that this vector u plus v is 25.4 degrees from u towards v. Okay, moving towards v. And that's the way that we can define direction when it comes to information given this way. Okay, similarly, for the subtraction, okay, I have u and v placed tail to tail, but now I know that the subtraction is the angle created by going tip to tip, from the tip of the second to the tip of the first. And so yet again, I've got a triangle that I can work with, except now the 40 degrees that I was given is in fact inside the triangle. So I can again use the cosine law. Okay, I found this angle here to be 106.9. So notice here, if I had used sine law, I would have not gotten the right answer. Okay, but because I'm using the cosine law, it automatically gives me the right answer. The question is how are we going to describe this angle? This vector is not up against the tail of v, and it's not up against the tail of u. So what I did is I took my resultant vector, and again, what can I do with vectors? I can just move them over. So I moved it over so that it's with respect to the tip of u. Okay, again, parallel line principle. The two obtuse angles are equal. So the way I described it is I described it as 106.9 degrees from u away from v, because I'm moving away from the vector v. All right, and so this is how I'm able to describe the direction. Okay, so a couple of things to keep in mind with these questions here is be very conscious about how the information is given. Take the information given, draw the diagram as needed, and then from there make any adjustments that you need. In this case here, I needed to adjust the fact that I couldn't work with the angle 40. I needed to move the vector over to place it tip to tail, and I had to calculate the vector that I was going to work with. All right, so the homework is already posted. Are there any questions on this page here before we kind of end it off? So somebody asks, would the angle be different if it was V towards U? Yes. So for example, we know that addition is commutative, right? So if I had drawn it so that it was V plus U, okay, yes, the angle would be different, but in the end, you might want to think about what the angles should add up to. I'll leave that as a I'll leave that up to you to think about how it would be related, because if I did V to U, okay, yes, you would get a different answer. Okay, another question we have is, so if the angles at hand are less than 90 degrees, then the sine law will only give us one answer. Yeah, so in the end, there are certain scenarios where you know that there's no ambiguous case. So my suggestion is, if you can use the cosine law, you don't even have to think about all of these. All right. So this is where I would suggest that if you can use the cosine law, just use the cosine law. Okay, because then you don't have to think about any of these issues regarding the ambiguous case. Okay, if you have to use a sine law because you have no choice and you're working with one angle and two sides, then yeah, you'll have to, you know, make sure you justify to yourself whether there might be any issues. Okay, anything else we want to ask?
Tony,
Yep.
can you repeat one more time why that inside angle is 140 degrees?
Yeah, so here, let me redraw it here. Let me get a piece of scrap paper here. So if I start off with okay, say, so this is 40 degrees. So what I want to do, if this is U and I want to add V, the idea is I want to draw them tip to tail. So I want to take this vector V and just move it over. Okay, so there's my vector V that I moved over so that now I can add these vectors tip to tail. Okay, is that okay? Okay. But now look at my triangle. This is the triangle that I'm going to be working with. This angle 40 is not inside that triangle. But look at these two vectors, both representing V. Because they're the same vector, they're parallel to each other. And I have a third line that's crossing them. And the parallel line principle tells us that all the obtuse angles are going to be the same, and all the acute angles are going to be the same. So this angle 40 would be the same as this here. And there's a relationship y between the obtuse and acute angles. We see that they're supplementary to each other. So if this is 40, then this would be 180 minus 40, so 140. Okay?
Perfect, thank you.
Okay, and now the other question is, Josh, on why we use the 40 degrees for subtraction. Okay, so let's kind of review that here. So here's my two vectors, U and V. Now I want to subtract the two vectors. So what is the vector U minus V? We saw that the vector U minus V, when the vectors are placed tail to tail, goes from the tip of the second to the tip of the first. So this vector here would be U minus V. But now I see that the triangle that I formed with U, V, and U minus V contains the angle 40 degrees. Okay, So we didn't have to make any kind of change like we had to do with addition, because that angle of 40 is already inside the triangle that's produced by u, v, and u minus v. Okay, does that make sense, Josh? Okay, great. And then here, Kieran asks, can we use either method for vector subtraction? Yes, of course. Now, I would say that when you have the vectors given with the angle between them tail to tail, it makes sense to use this method for subtraction. Okay, I would stick to, because automatically the subtraction between the two vectors gives you a nice triangle that already possesses an angle that you know. Okay, now when it comes to these examples where the vectors are given using cardinal directions, I would say, I don't know that one is easier than the other, so you can use either method. Okay. All right. Any other questions we want to ask? Okay, so again, please send, so we'll end the lesson here then. Please send any questions that you have via email, and I'm happy to post videos if you need them.